Hello, everyone. My name is George Bangle, and welcome to my Journal Club presentation on the fluid mechanics of tornadoes. Today, we'll explore what tornadoes are, how they form, and the key fluid dynamic principles that govern their behavior. We'll also look at tornado simulation models and an exciting hands-on experiment you can try at home. So, what are tornadoes? A tornado is a rapidly rotating column of air that connects the ground to a cumulonimbus cloud. They are capable of reaching wind speeds exceeding 300 miles per hour, although they typically last only a few minutes. Key stats include an average width of 500 to 1,500 meters, a duration between 5 to 10 minutes, but on some cases they may last hours, and a location in which tornadoes occur commonly is in Tornado Alley, which is located in the United States. Let's talk about some fundamental fluid dynamic concepts relevant to tornadoes. The first one would be vorticity, which refers to the local spinning motion of a fluid element. Higher vorticity indicates stronger rotational motion, which is crucial for the formation of a tornado. The second would be circulation, which measures the total rotation along a closed loop, helping us understand how rotation develops within the storm system. And the third will be the pressure gradient forces. As air moves from a high to low pressure, the steep pressure drop at the tornado center creates intense winds that spiral around it. These concepts are essential for understanding how tornadoes develop and maintain their strength. The formation of tornadoes can best be explained by breaking down various occurrences that later combine to form it. The first occurrence will be the different wind speeds at the, and directions at various altitudes that create horizontal vorticity. This is followed by strong updrafts from thunderstorms that tilt this horizontal vorticity into a vertical orientation, which forms a large organized rotating storm, which is called a mesocyclone formation, from which these tornadoes often develop. A key concept is that when air at the surface moves faster than air aloft, it generates rotational motion that can be turned vertical by thunderstorms, leading to a formation of a tornado. This image, although doesn't really show the wind spear process, it shows how the updrafts combine with the mesocyclone, or the updrafts combine to form a mesocyclone formation, which starts the beginning processes of a formation of a tornado. Since we identified the different stages in the formation of a tornado, let's now identify the key regions of a tornado once it's developed. The funnel cloud is the visual column of condensation and debris. The wall cloud is the area of lower pressure beneath a thunderstorm where tornadoes often form. And the mesocyclone is a rotating storm system that typically precedes tornado formation. The dynamics within these regions are crucial, especially the significant pressure drop at the tornado center, which creates high speed rotational winds around the low pressure core. The image on the right is a perfect diagram of both of those stages and the regions of the tornado, since it shows the flow of the air, the different flows of air that occur to create a tornado, as well as the different regions, the breakdown of the different regions of the tornado once it's formed. In this part, we're going to look at core equations that allow scientists to understand and predict the fluid dynamics within tornadoes. Each equation plays a unique role in describing how air moves, rotates, and changes in pressure inside a tornado. So the first governing equation will be the Navier-Stokes equation. This is the most critical equation in fluid mechanics. It helps describe how a fluid velocity changes over time and space. For tornadoes, these equations capture how the wind speeds up and circulates as it pulls towards the tornado center. The left side represents the acceleration of the air, while the right side involves forces like the pressure gradient, viscosity, and external forces which control how air moves and rotates within a tornado. The second equation will be the continuity equation, also known as the conservation of mass. The continuity equation ensures that mass is conserved, meaning the amount of air entering any point in the tornado equals the amount of leaving. This equation helps us track how air density and flow changes as the tornado grows and moves. When the flow speeds up near the tornado center, density may change, but the total mass remains constant. This principle keeps the tornado stable in shape, helping scientists understand airflow patterns. The third equation will be the viscosity equation, which focuses on the tornado rotation. The viscosity measures the local rotation in the air, and this equation describes how that rotation develops and strengthens within the tornado. High vorticity is what gives tornadoes their intense swirling motion. The first term on the right shows how air stretching in certain directions causes stronger spin. This rotation and spin continues to grow, making tornadoes more intense. The final governing equation will be the angular momentum. This equation is similar to a figure skater pulling in their arms to spin faster. As air gets closer to the center of the tornado, the radius decreases, causing the rotation to speed up. The angular momentum conservation keeps tornadoes spinning as they pull more air inward. This spin is maintained until external forces or changes in the storm disrupt it, ending the tornado. In correlation with tornado simulation models, the Fujita scale uses the wind speed to measure the intensity of the tornado. The Fujita scale ranges from EF0 to EF5 based on the damage they may cause. EF0 is typically wind speeds of 65 to 85 miles per hour, which refers to minor damage. EF1 is wind speeds of 86 to 110 miles per hour, which is moderate damage, and EF5 is wind speeds of 200 miles per hour, leading to catastrophic damage. Understanding these fluid mechanics helps explain why higher wind speeds result in greater damage, which is directly result to the increase of kinetic energy with the square of the wind speed. Computational fluid dynamic models, or CFD, are essential tools for simulating tornado formation and movement. By using these models, scientists can better predict the intensity and path of tornadoes. CFD models are primarily built on the two of the fundamental equations of Navier-Stokes equation and the continuity equation. With these equations, CFD models help us calculate wind speeds and pressure changes at different points within the tornado vortex. This gives researchers a detailed picture of the tornado's dynamics and potential areas of impact. One key assumption is that the air density remains constant within the tornado. While this makes calculations simpler, it is not always perfectly accurate, as the air density can fluctuate with temperature and pressure in real-life tornadoes. However, even with these simplifications, CFD models are still powerful tools for advancing our understanding of tornado behavior and helping us make better predictions. The majority of observed tornadoes are cyclonic, but some are anticyclonic tornadoes. In this simulation, an anticyclonic tornado occurs first, then decays shortly before a multi-vortex EF5 strength cyclonic tornado forms. The blue indicates negatively buoyant air, which is cool or dense, while the yellow-red indicates positively buoyant air, which is warm or less dense. So a simple experiment that can be conducted at home is the tornado in a bottle experiment. The materials needed is typically two bottles. Fill one bottle with water, typically 1/2 to 2/3 full. A washer, duct tape, and if you want, you can add food coloring or glitter to better see the tornado. So the instructions are to fill one bottle with water, place the washer over the opening of the bottle, invert the second bottle and place it over the first, securing it with duct tape, and then quickly turning the bottles upside down and swirl them to create a tornado effect in the water. This experiment visually demonstrates the principles of vorticity and rotation, just like what happens in a tornado. In conclusion, tornadoes are fascinating phenomena that exemplify the principles of fluid dynamics. By understanding the mechanics behind their formation and behavior, we can improve forecasting methods and even conduct engaging experiments at home. Thank you for your attention, and I welcome any questions you may have. Thank you.